Welcome to part three of the Earth Science atmosphere discussion. So, in the previous part two of the atmosphere, we looked at the latent heat, the concept of latent heat, where energy is either released or absorbed during a phase change, and particularly the phase change between water. And we took that relationship of the various phase changes and applied it to humidity, relative humidity, and dew point. In addition, we also looked at how to calculate relative humidity. Also, we took a little look at the greenhouse effect as well, and understanding that the greenhouse is a natural process and very necessary to keep the Earth warm. And again, if it wasn't for the greenhouse effect, average temperatures would be minus 15 degrees. So I want to continue in the discussion of the atmosphere with the formation of clouds. So again, we're going to also apply the latent heat concept, and we're going to look at the adiabatic principle, condensation, and then at the very end of the discussion, we're going to put it all together and look at why, for example, Bakersfield experiences the type of climate year-round that we typically do. Hot in the summers, cool in the winters, and barely a spring or a fall. So this particular slide I thought was interesting because it shows, of course, different types of cloud formations, which is all directly related to this process called adiabatic principle. And I am particularly like this particular formation where it looks like a tiger. In fact, I would encourage all parents who have children to take a Saturday morning or Sunday morning, nice day, lay out on the lawn with your child and look at clouds and ask your child what they see in terms of different clouds formations. And if you do that, you really get an insight of what your child is thinking. I know that I do that with my 15-year-old daughter, and some of the things she comes up with is very interesting. So we're going to look at a concept called adiabatic processes. And adiabatic processes describes the temperature of an air parcel and how this temperature changes with respect to the air parcel rising and falling within the atmosphere. And when we talk about winds in the next discussion, I'm going to bring up an analogy of the atmosphere behaving like a boiling pot of water. And so, for example, if you take a Pyrex dish that's filled with water and you begin to boil it and you look through the boiling water, you see bubbles rising and falling. And really, your atmosphere is very analogous to that pot of boiling water. But when you look at that boiling pot of water, in your mind, slow down the bubbles really, really, really slow. And what happens is you begin to get these bubbles that rise up really slow and sink really slow. And that's actually what takes place in our atmosphere, but not water, but in this case, air. And so air bubbles or pockets or air parcels will have a tendency to rise. And as they rise, sometimes they'll fall. And that process of rising and falling changes the weather, if you will, in the atmosphere. And really, we can't see the bubbles rising and falling, but we certainly can feel the effects of it. And so one of the common processes involved in that rising and falling air parcels is adiabatic processes. So what we're going to do then is we're going to take a parcel of air, and this parcel of air on the surface has air molecules that are very tightly closed and pushed together. And it's the pocket of air then at the surface is going to be very small because you have the weight of the atmosphere sitting on top of that particular air parcel. And we're going to allow this air parcel to rise in the atmosphere. And as the air parcel begins to rise in the atmosphere, the weight of the atmosphere decreases, or atmospheric pressure decreases, and the air parcel begins to expand. So if you watch my air parcel at the bottom, we allow the air parcel to rise. In fact, what we can do is we can count these little air molecules that I put in the bottom of the air pocket, and there's 16 of them. And so we're going to maintain that 16 molecules for our example purposes as we allow this air parcel to rise. And we would expect, again, under adiabatic conditions, that as the air parcel rise, it'll begin to expand. And what I want you to take note of is what happens to the spacing of the 16 molecules. So we have an air pocket on the bottom, it's going to rise, and as it rises, it still does have the 16 molecules in there. But what has happened? They've gotten farther and farther apart. We'll allow the air pocket to rise again. Same air pocket, same 16 molecules. And again, the space in between the molecules have gotten higher. And I think we'll do it one more time. And so now it's rising in the atmosphere. And again, what you're experiencing is the air pocket as it rises is expanding and expanding, and the molecules are getting farther and farther apart. So adiabatically, what takes place when air rises and expands is air will have a tendency as it rises and expands, it begins to cool. So we can say rising, expanding air adiabatically cools. And it cools because the molecules are being separated farther and farther apart. Conversely, we can go the other way adiabatically, and as air sinks or subsides, then the air molecules get closer and closer and closer together, and we would say that air is compressing, and air will have a tendency to warm. So basically, adiabatic processes represents rising and falling air that cools upon expansion and warms upon compression. So, by definition, adiabatic processes involve no heat exchange between the parcel of air and surrounding atmosphere. And when we say no heat exchange, we're talking about the sun's influence. Now, the sun influences the warming of the air at the surface, but as it rises or falls within the atmosphere, again, it'll either adiabatically cool or adiabatically warm. So cooling and heating take place very fast. So rising air expands and cools adiabatically, subsiding air or sinking air compresses and adiabatically warms. And there's some pretty good examples of this that we've all been familiar with. For example, if you've ever gone down to a store that sells computer type paraphernalia, and you buy this compressed can of air that cleans keyboards. And if you ever noticed that when you're cleaning the keyboards with this compressed can of air, as you're spraying, if you ever notice, the can gets really cold very fast. Same thing if you use a hairspray, and so it cools very fast. And what's happening is the material inside the can is expanding at a fast rate, and so the can basically is adiabatically cooling. And on the other hand, I like to restore cars, and I have a shop with an air compressor in my shop. And one day I was starting the air compressor up, and it was running for 15 or 20 minutes, getting air in the tank. And my son comes over and leans up against the tank and says, "Wow, this tank is really hot." And I said, "Well, what's happening is the air is being compressed, because hence the air compressor. The air is being compressed, and upon compressing, it's adiabatically warming." Pardon me, take a drink there. So again, rising air expands and cools adiabatically, subsiding air compresses and adiabatically warms. So we can use adiabatic processes to measure and predict air temperatures, for example, as air goes from the bottom of a mountain and rises toward the top of the mountain. So we have two types of scenarios that we're going to use to measure the temperature of an air mass going up a mountain. And in the first situation, we're going to use an air mass in which we call it dry air. And we're going to use what we call the dry adiabatic rate. And we're going to follow this air mass and predict the temperature under dry adiabatic rate conditions. Dry adiabatic rate conditions say that we have unsaturated air. We say unsaturated, meaning that the air water vapor content is below relative humidity 100%. So it's not fully saturated. And so given unsaturated air, it will cool 10 degrees for every 1,000 meters. Now remember, that's going up the hill. Let me repeat that. Going up the mountain, so air is rising, so it's going to adiabatically cool. And under the dry adiabatic rate condition, it's going to cool at 10 degrees per 1,000 meters. On the other hand, if air was allowed to sink and subside, air would warm 10 degrees per 1,000 meters under the dry adiabatic rate. So we're going to take some air. It's at the bottom of this particular mountain here. And right now the temperature is 12 degrees centigrade. All right, 12 degrees. And we're going to allow this air now to rise another 1,000 feet to the 2,000 feet. I'm sorry. We're going to allow this air to rise 1,000 meters to the 2,000 meter mark. So again, the 2,000 meter mark. And we should be able to predict the temperature of this air parcel given the dry adiabatic rate of 10 degrees per 1,000 meters. So where my arrow is going to be the new air parcel at the 2,000 meter elevation. And what would be the temperature? Hopefully you're predicting the temperature would be 2 degrees centigrade. Why? Because it went up 1,000 meters, and at 1,000 meters, it's going to cool 10 degrees. So 12 minus 10 is 2 degrees. So it definitely adiabatically cooled and got cooler. Now let's allow the same air to rise another 1,000 meters to the 3,000 meter part of the mountain, so the very top of the mountain in this case. And again, under dry adiabatic conditions, using 10 degrees per every 1,000 meters, what would be my new temperature at the 3,000 meter mark? So in this case, you're going to go 2 minus 10 degrees, and you should come up with a minus 8 degree centigrade. Okay, so you can see the air has done a couple things. As the air rises up the mountain, the air expands and it adiabatically cools. The second characteristic is that under the dry adiabatic rate, the air is cooling 10 degrees per 1,000 meters. So in this case, the final temperature at 3,000 meters is minus 8 degrees. Now, where do we see this at? Well, you see it wherever you go to the top of mountains. And I'm sure most folks that have driven from Bakersfield and went to the top of a mountain range, you get out of your car, you say, wow, it feels a little cooler up here. And that's very typical because air is adiabatically cooling as you go up the mountain. Case in point, the Tehachapi area is consistently about 10 degrees less than Bakersfield. If it's 100 degrees in Bakersfield, it's 90 in Tehachapi. 30 degrees in Bakersfield, it'd probably be 20 in Tehachapi. The point is that Tehachapi lies at an elevation where adiabatic cooling takes place and keeps Tehachapi at least 10 degrees cooler than Bakersfield. So this is the dry adiabatic rate, 10 degrees per every 1,000 meters. Now, what if we allow the air to, in this case, to be saturated? So now the air is going to have moisture and relative humidity is going to be pretty close to 100%. So in this case, we're going to use our same mountain, but now we're going to look at the air parcel if it is saturated. And this is known as the moist adiabatic rate, or the MAR. Under moist adiabatic rate conditions, for every 1,000 meters, temperature can vary between 4 and 10 degrees. However, and that's going to depend on how saturated, how much moisture. But we're going to use 5 degrees because that's basically represents the average, and it's easier to do the math. So we're going to say that on average, for every 1,000 meters, there's going to be a 5-degree change in temperature per 1,000 meters. So let's go back, and we'll come back down to this part. We'll come back down to the bottom of the slide here in a minute. So let's take a look now at our same air mass that we used in the previous slide, where we had the temperature at 12 degrees when the air mass was unsaturated. Now we're going to use 12 degrees for a saturated air mass. We're going to allow it to rise 1,000 meters to the 2,000 meter mark. And what will be my new temperature under the moist adiabatic rate? So it's going to rise 1,000 meters at 5 degrees per 1,000. And the new temperature is going to be 7 degrees Celsius. So here we got 7 degrees Celsius and at 2,000 meters. If we allow the air to rise to the 3,000 meter mark, then we're going to take another 5 degrees at 3,000 meters, and our final temperature at the top of the mountain under saturated conditions is now 2 degrees. Now, recall that in the previous slide, the final temperature at 3,000 meters was minus 8 degrees Celsius. Yet, with a saturated air mass, the temperature is 2 degrees Celsius as our final temperature at 3,000 meters. So there is a difference. In fact, with the moist adiabatic rate, the temperature is a lot warmer, 2 degrees, than it would be if it was dry air at minus 8 degrees. So the answer is why. And the answer looks at the relationship between the adiabatic process and latent heat. So for example, if we are at 100% relative humidity in the moist adiabatic rate scenario in this particular slide, then what is happening with respect to latent heat? Well, we have reached dew point. We've already begun condensation. And so we're moving from a vapor to a liquid. And what happens with latent heat under the conditions of moving from a vapor to a liquid? Well, latent heat is being released, right? So under that phase change, vapor to a liquid, latent heat is being released. And upon releasing that latent heat, it actually warms the air up. And so that's why at the top of the mountain under moist adiabatic rate, we end up with a 2 degree as opposed to a minus 8 degree in the previous slide. Now, I don't know about you folks, but minus 8 and 2 degrees is still cold for me and probably for a lot of us. But again, the processes don't care about how we feel. And so it's all relative. But in fact, it is warmer with 2 degrees than minus 8 degrees. So we come back down to this last part of the slide, and it says, why is the dry adiabatic rate different from the moist adiabatic rate when it becomes temperature? And it depends on the water vapor content of the air. More vapor, the more latent heat exchanged. So for testing purposes, you need to look at these two slides and study the process on how these temperatures, how we arrived at these particular temperatures using the dry adiabatic rate and the moist adiabatic rate. So let's now then turn our attention to clouds. And as we talk about clouds, we're going to be, again, going back to looking at adiabatic processes and heat exchanges and latent heat and so forth. But let's look at really what a cloud represents. And a clouds represent suspended water droplets. And notice I said water droplets. And these suspended water droplets can come in the way of ice particles, mixture of both, and so forth. But to produce a cloud particles usually grow around small, tiny pieces of matter, which we refer to as condensation nuclei or nuclei. And what natural way then for the Earth to produce small pieces of solid matter, which are known as aerosols or condensation nuclei? What natural way to put these small bits of matter into the atmosphere? And that would take us to the ocean. So most of the condensation nuclei originate from the ocean, and it originates from the ocean in regards to salt particles, which come in the way of ocean spray. So for example, I have a picture down here, an image down here showing the ocean, showing the waves breaking through, and have the waves break through and kind of merge up into the atmosphere. The spray is carrying little salt crystals, little salt particles, and those little salt particles have water around them, which evaporate and then become, a single little salt particle. And those salt particles are typically lifted into the winds and lifted up into the atmosphere and act like little condensation nuclei. And so you can see down at the bottom of the screen, it's droplets of spray are lifted by wind currents, and upon evaporation, again, the salt crystal, an XL, by the way, means crystal, is left behind to form condensation nuclei. And so that's how we're going to begin making a cloud. This next slide now shows how the Earth's atmosphere can form a cloud. And this is a very important slide because this slide packs a lot of information with respect to cloud formation. So I'm going to try and go through this slide, and we're going to bring into this slide everything we've learned about humidity, relative humidity, dew point, and I'm going to introduce to you some other terms. And what I'd like you to be able to do is to, when we're done with this slide, is to be able, before the exam, is to, in your own words, describe how clouds form using the terminology, again, as relative humidity, condensation, dew point, and so forth. So let's start then by looking at the bottom of this slide, and let's look at the air parcels. And what you see is some air parcels. Here you see an air parcel at 32, 22, 12, which is the same air parcel. And we're going to allow this air parcel to begin to rise. And so right now it is at 32 degrees centigrade. And right now at 32 degrees, relative humidity is down, meaning that this is enough temperature to hold more water vapor, if you can get more water vapor into it. But right now, relative humidity is down. Now this water, or this air parcel, is going to begin to rise. As the air parcel rises, what happens to the air parcel adiabatically? Well, you come over here, and we would say that the air parcel adiabatically begins to cool. And in this case, they're using the dry adiabatic rate. So we're cooling it from 32 degrees at 1,000 meters. It's now 22 degrees because we're at 10 degrees per 1,000 meters. And now we're going to cool it at 2,000 meters height, and that's cooling down to 12 degrees. So while this air parcel is cooling, what is happening to the relative humidity? Well, the relative humidity is going up. It's getting closer and closer to 100%, right? Because remember, humidity is dependent on air temperature. And the cooler the air parcel, the less moisture it can hold. And conversely, the warmer the air parcel, the hotter, or warmer the air parcel, the more water vapor it can hold. So it collected a lot of water vapor down here at 32 degrees centigrade, but now as it begins to adiabatically cool and rise, that water vapor it collected here at 32 degrees is becoming more condensed and more full and more full. And finally, let's say in this example, we reach 2 degrees centigrade. And let's say for this example that the dew point for this particular air parcel was 2 degrees, meaning dew point, the temperature at which relative humidity is 100%. So here, then we reach 2 degrees, the air parcel cannot hold any more moisture, relative humidity is now 100%, saturated. And at that point, we move from a vapor to a liquid. And as we move to a liquid, a cloud is formed. And typically, a cloud will form along an altitude height known as the LCL. And the LCL stands for lifting condensation level. Let me repeat that. LCL is the lifting condensation level, which means any air that rises above the condensation level is going to convert from a vapor to a liquid and form a cloud. In fact, one should be able to go outside, look at the cloud formations in the atmosphere, and many times we see where the clouds have formed flat bottoms. And it almost looks like someone is taking a knife and cut along those flat bottoms. And really what you're looking at is the LCL. You're looking at the lifting condensation level. You're looking at the height in which dew point has been reached and in which relative humidity is 100%. So when one says, how does a cloud form? One should say, well, as air rises, it adiabatically cools, relative humidity increases, relative humidity begins to approach 100%. Finally, at some height, it reaches dew point, the temperature at which relative humidity is 100%. And then at that point, the water vapor will condense, and then it will move from a vapor to a liquid, thus producing a cloud. And the cloud sits right on the LCL, lifting condensation level. So this is a very important slide for folks to study, very important slide for folks to rehearse in your mind, in your own words, how clouds form, and using the terms relative humidity, LCL, 100% saturated, dew point, condensation, and so forth. So this is a picture of a cloud forming. And what I try to do in this picture is to map the LCL, and you can kind of get a good idea that the LCL is marking the base of the cloud, meaning that any moisture that, here it comes, any moisture that begins to rise. So we have air parcels that are filled with moisture. As it rises, adiabatically cools, relative humidity goes up. It reaches the LCL at 100% relative humidity, reaches dew point, and then it condenses, and now we have a cloud. And so really a cloud is a function, once it gets to the LCL, it's a function of condensing. It's a function of condensing where vapor moves to a liquid. How about what happens to a cloud once it passes the LCL? In other words, what's going on inside the cloud? So in this example, remember that on the LCL, and this is very important, once condensing takes place on the LCL itself, when we move from a vapor to a liquid, what is being released? And you should be saying, wow, that's latent heat. Because remember, we move from the phase of a vapor to a phase of a liquid. Latent heat is released. That latent heat creates a warmed area along the LCL. And then what happens then is that warm air wants to rise. And as that warm air rises, it takes with it the moisture, which starts building up these big bulbous cumulus type clouds. Once the air is away from the LCL, then air begins to sink and it comes back down and gets warmed up again. And then actually inside the cloud, you're building up what we refer to as convection cells. And remember from plate tectonics, we talked about the convection process in the mantle that drives the plates. Convection works the same way, but this time it's convection in a gas as opposed to convection in a liquid, or I should say convection for the clouds. It's convection as a thinner liquid. So convection in this hot air rises, and then cooler air sinks, and it creates a lot of convection currents inside the cloud itself. In fact, if you've ever taken a commercial flight in an airplane, and for the long distance in the airplane flight, you're flying in the stratosphere. And then as the plane needs to land, what button and what light appears, where you're sitting in the plane as you start to descend, towards the airport. It says fasten your seatbelts, because in many cases the plane has to move from the troposphere into the, it moves from the stratosphere into the troposphere. And if you fly inside of a cloud, you're going to meet with a lot of convection cells and uplifts of air currents and so forth. And of course, you're going to have turbulence. And that's what the pilots like to avoid, is turbulence within the cloud. But I think, and I'm not a pilot, but I'm sure that's why most pilots like flying their airplanes above the clouds in the stratosphere, for example, to stay away from that turbulence. This last slide in our atmospheric discussion deals with the climate that we observe in our Bakersfield area. And so we're going to go through and look at why we experience the climate in Bakersfield, and then we're going to make a relationship between that and cloud formation under adiabatic conditions. So for example, we start off with a cross-sectional view of California. And we mean cross-sectional view by taking a slice of California and looking at from the side. So here you can see we have the Pacific Ocean here, and then we have the coast ranges, which is a mountain range along the California coast that probably gets up to about a couple thousand feet in elevation. Here would be the San Joaquin Valley, and then as we move up the western side of the Sierra Nevada mountains, this would be the Sierra Nevadas, which would get probably about 10 to 12,000 feet in elevation. This is a map of California, so this is an aerial view of California. Here would be the Pacific Ocean. Here would be the coast ranges. Here would be the San Joaquin Valley. Here would be the Sierra Nevadas, and over here is the Mojave Desert, which in this cross-sectional view is the Mojave Desert. So what we want to do is we want to follow an air mass that's moving off the ocean onto the west coast of California. And we're going to watch this air mass and see what the behavior of this air mass is, which will dictate the typical climate and weather that we experience in Bakersfield. So just to make sure we're all know where we're at, let's go ahead and put Santa Barbara here, which is on the coast. And let's put Bakersfield here in the San Joaquin Valley. And by the way, this is not to scale. And let's allow evaporation to take place in the ocean. And, we have to realize that, first of all, the oceans make up 70% of the surface area of the Earth. And so 24/7, there is copious amounts of evaporation that take place on the ocean surface. So the atmosphere is constantly and continually being filled with water vapor through evaporation. And let's allow this air mass now that has now taken on water vapor with, from evaporation. And let's allow this air mass to make its way now. So it's a air mass that's has moisture in its air. And we're going to allow this air mass to move on the coast of California. Now, the first thing it's going to do is it's going to come in contact with the west side of the coast ranges. And so if we follow my arrow and the air mass is down here, as it comes in contact with the west coast of the coast ranges, the mountain is going to force the air to have to rise because it has to go over the mountain. So as the air rises, what do we know happens? Well, you should be saying, as air rises, it adiabatically cools. As it adiabatically cools, relative humidity goes up, reaches dew point. Upon dew point, the air is saturated and the air is condensing. And so typically we're going to see rain and clouds form on the west side of the coast ranges, right? And that's typical. Now, if we continue with this air mass, and we continue this air mass where it comes over the coast ranges, and so as the air mass comes over the coast ranges, Now it begins to subside or sink, and what happens to it adiabatically when air sinks? When air sinks, it's now going to compress the air mass, and upon compressing, it's going to adiabatically warm. And so, in terms of getting rain in the San Joaquin Valley, you're not going to get as near as much as you would on the coast. In fact, Bakersfield sits in what we call a semi-desert. We get a little bit more rain than a desert. We're not quite a desert, but we don't get a lot. So we sit in this area called a rain shadow. And a rain shadow is governed by the fact that this mountain range is creating a shadow or blocking the moisture. And again, it's warming due to adiabatic compressing. Well, now this same air mass still does have moisture in it, and now the air mass has to now get over the Sierra Nevada mountain range. And so as it goes over the Sierra Nevada mountain range, the high mountain range at 10,000 feet elevation is going to force the air to move up the westward side of the Sierra Nevada mountains. So what's going to happen? Here we go again. Air rises. Air adiabatically cools by expansion. Relative humidity goes up. It's reaching dew point, which is relative humidity at 100%. And upon dew point, it's going to produce clouds along the LCL. And in most cases, you may get some rain. So here the air is rising. And then typically what you have is lots of precipitation along the western side of the Sierra, the mountain range. Now, again, this air has to continue, and as it continues over the top of the Sierra Mountains, then it's adiabatically going to warm. Air is going to be compressed, and over here we produce a true desert in the sense that they get less, I believe, than 3 inches of rain per year, and this would be the Mojave Desert. And so if you come down to the map of California, again, you can see coast ranges get rain, and we can see that the San Joaquin Valley does not get rain in terms of Bakersfield. The Sierra Nevada mountain range gets rain, and then the Mojave Desert does not get rain. This type of weather climate pattern is known as, if you come up here with my arrow, it's known as orographic precipitation, which basically means that the mountains are producing blocks, if you will, or blocks the moisture from getting into the valleys, which creates rain shadows. So again, we have a rain shadow in Bakersfield, and we have a rain shadow in the Mojave Desert. And so this really is a contributor to the type of climate that we see in Bakersfield, where it's basically very, very hot in the summertime because we're away from the ocean. And because we're away from the ocean and because of orographic precipitation, it's very cold in the wintertime. And rarely do we get a lengthy spring or a lengthy fall. So for exam purposes, one should be able to draw this cross-sectional view of California, and in your own words, you should be able to explain what happens to a parcel of air as it leaves the ocean and makes its way across the state of California. And you should be able to incorporate why clouds form using adiabatic processes and relative humidity concepts and dew point concepts.